So area bounded by a single polar curve. So in geometry, we learned that the area of a sector, or basically a slice of a circle, is going to be formulated by this 1/2 theta r squared. So it kind of has this pizza wedge look to it. R equals f of theta. Radius is some function of f of theta in terms of theta. So this is similar to adding infinite numbers of rectangles for rectangular area. So rectangular area looks more like this, right? Where you have a curve like this and you're adding these infinitely thin rectangles from one end to the other. But the adjusted formula, which we're not going to go through a whole limit definition here, but it's basically 1/2 delta theta, f of theta sub I squared. Before it was like dx and f of x dx, but now we're adding these infinitely thin sectors, and all these sectors are going to be stemming from the same origins. So we're just kind of fanning out from one end to the other. So that's something to kind of get used to, that it's not like rectangles where every rectangle has a different region. But this one is all stemming from the same point. So we're finding the area of this infinitely thin sector, then we're moving on to this one, and we're kind of fanning out in a counterclockwise direction. So here's the limit definition, but what we're going to use is this one here. Okay. This one is the adapted area formula, and basically, I think the hardest part of these types of problems is trying to figure out where your bounds are going to be, because the rest of it is just calculator and entry into the calculator if you know what R is. So yeah, I think the hardest part is figuring out, where does the graph begin, where does the graph end, and we'll talk about those skills. Yeah.
On the central angle, what is the symbol?
Yeah, so this is kind of like width. You know how width is b minus a over n from our limit definition. So this is kind of like the same thing. It's like b minus alpha. That's kind of like your lower and upper bound. Yeah. So so instead of width in terms of rectangle, now it's going to be delta theta in terms of theta. We're taking the entire theta region, and then we're splitting up into minuscule thetas. So we're essentially adding infinitely thin sectors to generate the exact area of this polar region. Okay. All right, let's look at number one. Find the area bounded by r equals 5 sine of theta. And you know that your sine curve is going to, well, your sine theta is going to be a circular graph. And just to kind of get an idea, right? If I were to plug in 0, I'll start at 0. And then if I plug in pi over 2, I'll get 5. So this circle is kind of going around in this direction here. That's not ready. not indicating exactly where that origin is, but it's here. And then by the time it reaches pi, it's going to be back at 0. So we know that this circle is going to complete its full rotation between 0 and pi. And so imagine this is happening. We're accumulating these area regions starting here, and then we're creating all these sector regions from one end to the other. So then our area is just 1/2 integral from 0 to pi. We're adding these infinitely thin sector regions from 0 all the way to pi, and then 5 sine theta squared d theta. You practice plugging this in your calculator. Now, you don't have to be in polar form in order to plug this in. You can be in rectangular form. You'll get the exact same answer. So it's probably easier to just leave it in rectangular form. And you can do math 9. I can have my y1 hold my 5 sine theta or 5 sine x. And I forgot to put a 1/2 in front, so I'm going to say times 0.5. I don't have to add pi or anything like that. It's just my area is simply that 19.635. Number 2, find the area of the shaded region in the polar curve from of 1 minus cosine of 2 theta. So here's my equation. Now notice that there's 2 petals here, and this doesn't quite match what we know to be true, right? Normally, if it's cosine 2 theta, we expect 4 petals, but that 1 minus kind of throws things off. But really, we know that there has to be some polar zeros in order for that region to get closed off. So the strategy here is, if we can look for polar zeros, then we know the distance from one polar zero to the other polar zero is going to cause the closing of one region. Okay. So what if we look for polar zeros? Polar zeros would be where the radius is 0. So I can set this up and look for this algebraically. So when is 1 minus cosine 2 theta equal to 0? Let me solve this with a positive cosine 2 theta. Now, we don't want to have to, we can avoid double angle identity by using inverse trig here. So what if we just did move that cosine over and ask ourselves, okay, when is cosine equal to 1? When is cosine equal to 1? Cosine theta is equal to 1 when theta is what? What's one option? 0. Where else? 2 pi, yeah. And if I keep going, maybe 4 pi, 6 pi, but I don't have to go that far, I don't think. So if I want to solve for theta, we just divide everything by 2 or multiply by 1/2. So I get 0 pi, 2 pi, and 3 pi. Now we could pick these intervals that are past pi and 2 pi because it'll just continue to overlap the same regions. But we can just find two consecutive, right? We know that initially it's going to start here at pi. It's going to have to come back to a polar 0. So then between 0 and pi, that should be, if we're starting at polar 0 and ending at, and then the next interval is also polar 0, that's where that interval is going to get closed off. And if you went from pi to 2 pi, then you'll be finding this bottom region. And that's fine as well, because a lot of these polar curves are going to be symmetrical. But I just think it's more straightforward to just go from 0 to pi. So this is the way that you would write on paper, but in your calculator, you can do everything in terms of x. You don't have to be using you don't have to be in polar form with theta to get the same answer. Let me see. Oops, sorry, I typed it in wrong. 1 minus cosine of 2x. There we go, 2.356. Right, questions? Number 2? Yeah. Oh, you mean between all these intervals here? So, well, we can sketch the graph out. We know that we're going to start here. At pi, we have to come back here as well, because all these are places where polar 0 is going to be reached. So from 0 to pi, and then from pi to 2 pi, and from 2 pi to 3 pi. So basically, any of the intervals will get you consecutive polar zeros, and consecutive polar zeros will get you one of these regions. So it technically doesn't matter which one you choose. You're going to get the same answer. It'll be from 0 to 2 pi. Yeah, let's try that. We should get double the solution. Yes, great. We did. Yeah.
Thank you.
Yeah, and then a big feature of polar is we're going to try to use symmetry as much as possible, because everything that we see, they're symmetrical. So basically, sometimes we can even just find half of something and then just duplicate it to the size that we want to see. Okay, and I'll show you what I mean by that when we're dealing with petals. All right, any other questions? All right, let's go to page 46. Okay, find the area of the inner loop of the limacon. R equals 2 cosine theta plus 1. So just to have an idea, if I plug 0 in, 2 cosine of 0 is 1, 1 plus 2 is 2, 2 plus 1 is 3. So we're starting here, and the graph is moving this way. It's moving this way. It's going to hit a polar 0, and then it's going to loop in, and it's going to hit a polar 0 again, and then it's going to finally complete this whole cycle between 0 and 2 pi, right? But the advantage here is that we're only looking for this inner loop here. So if I can find two consecutive polar zeros, I know that the range between those two polar zeros is referring to that region in between. So if I can find my two polar zeros, then I know where my inner loop is going to exist. So let's find our polar zeros. So polar zeros is whenever your radius is 0. So let's look for that. Okay. Where is cosine equal to -1/2? And 4 pi over 3, yeah. Second and third quadrant, right, in that pi over 3 family. So if we know that we're going to hit 2 pi over 3 and 4 pi over 3, we know that between these two polar zeros, that's when that inner loop is going to get closed off, and that's the region that we're looking for in terms of our area. And the rest is just calculator. So we're really not doing much calculus, right? We're making the calculator do all the calculus for us. It's just how well do we know how the graphs are formed, and can we figure out what the bounds are? That's really the most challenging part of this section here. It's not even the calculus. Number 4, find the area of one petal of the rose curve. R equals 3 cosine of 3 theta. Right. Now we know what's happening here. We know that we're expecting 3 petals. Now the graph is drawn for us. That's nice, but we know the petal each has a length of a diameter or a length of 3, right? Let's find our, so the idea is, well, if we can find our polar zeros, then we know that when we know where our graph is going to get cut off, right? If we see 2 consecutive polar zeros, we know that it's going to be one full closed off region of the petal, right? So again, polar zeros is going to make things easier for us. Divide by 3, I can get the 3's to go away. Cosine of 3 theta is equal to 0. I don't, I'm not going to use messy trig identities. I just want to use inverse trig for me to get that 3 theta isolated. So when is cosine equal to 0? Pi over 2, where else? Pi over 2. I can keep going if I want to, but we don't have to, but we can, yeah, we can say 5 pi over 2, 7 pi over 2. Okay, multiply it by 1/3 or divide by 3. So theta is pi over 6, 3 pi over 6, which is pi over 2. I don't have to go that far. I just wanted to show. So really, any consecutive polar zeros is guaranteed to close off a full petal for us, right? So you can either do from pi over 6 to pi over 2, pi over 2 to 5 pi over 6, 5 pi over 6, 7 pi over 6, right? Those between those intervals, anything that's between two polar zeros is guaranteed to close off a full region for us. So I'm just going to target the first two. So from one polar zero to another polar zero, it's going to give us one closed petal region. I want to give you, well, first of all, any questions with this so far? Just want to give you some options in terms of, there are other ways for us to find petal. What if we wanted to somehow involve zero, or in terms of theta zero? Now, not every graph starts at the polar zero, right? This doesn't start at polar zero because at degree 0, where's my graph starting at? Cosine of 0 is 1. 1 times 3 is 3. So the graph starts here, right? And we know the graph is going to continue moving until it hits its first polar zero, which is at pi over 6. So is there a way for us to find a petal if we just know that this region is giving us from 0 to pi over 6? Yeah, good. So from 0 to pi over 6, basically it gives us half a petal. So we can use symmetry to help us, right? If I know what the area of half a petal is, I can figure out the area of the full petal. So we can do this as well. We know that ultimately we're going to be doubling our results because the area that we're finding is only half a petal. So 1/2 integral from 0 to pi over 6 r squared d theta. And so I just want to give you as many kind of ways to look at problems, because sometimes it's easier to just do half of the problem and then just double it. Or maybe you want to use the strategy to find all 3 areas of the petals. And if you have half of it, you can just 1, 2, 3, 4, 5, 6 multiply by 6, and that'll get you the areas of all 3 petals. Right? So you can either, strategy is sometimes it's easier to look for the area between 2 consecutive polar zeros. Sometimes it's easier to look for half of something and then just double it. So I just want to give you, all the different variations here, and then you can decide how you want to approach a certain problem for on the test or quiz or AP exam. Okay, try number 1. Number 1 is going to feel like number 3 above, so see if you're able to apply that strategy for number 1 on bottom of page 46. So our strategy from number 3 above was to look for consecutive polar zeros. Because we know consecutive polar zeros is going to close off that region that we want to look for. Okay, so the polar zeros that I found was 7 pi over 6 and 11 pi over 6. Since that is where sine is going to be negative and negative 1/2 in that pi over 6 family, third and fourth quadrant. And then once you have your bounds, it's easy. Just put the formula into your calculator, right? Number 2, find the region enclosed by the cardioid r equals 2 plus 2 cosine theta. You know that anything that is in the cardioid family is going to have, it's going to complete a cycle from 0 to 2 pi. Anything that is in the circle family is going to be from 0 to pi. And then if it's a double angle or even pedals, then it's going to be 2 pi. But odd pedals will be from 0 to pi. But if you're, if you're for some reason you're unsure, how long that interval is, you can always test it out, right? Test it out. If a cycle is going to end, it's going to have to end in the same place that it started, right? So pi is not far enough, because if I plug pi in for theta, I'm not getting my radius of 4. It's not until 2 pi that I'm able to get back to my starting point. So that's a way to check that that you've completed your full cycle if your starting and ending point are the same location.
Would it not be -1 and then use pi and 3 pi? Plug in 0 for r.
Yes, the full cycle. Yeah, you can start drawing the graph before 0 if you want. So if you want, is that what you did from -1 to 3 pi?
Yeah.
Yeah, you get the same answer, because you're just starting at a different point, but you're still achieving the full cycle. But yeah, I see your strategy. you're looking for polar zeros and you're starting and ending at the polar zero, and that's just perfect. Yeah. Okay, number 3, page 47. So number 3 is probably not a good strategy to look for your polar zeros because number 3, 4 plus 2 cosine theta is going to be a dimpled limacon, so you're not going to be able to find a polar zero. But if you know that a limacon and cardioid that they all have a cycle from 0 to 2 pi, then you can jump directly into from 0 to 2 pi and just set that up. But yeah, a lot of these problems is if you can find consecutive polar zeros, a lot of times that is the region that you're having to find the area for. Yeah, so if a problem ever says find the area of one pedal or find the area of this one loop or this other loop, yeah, look for consecutive zeros, and a lot of times that is where your solution can be. For number 5, we may not know exactly what a lemniscate looks like, but if I can find consecutive polar zeros, that's going to have to be one loop. And the loops of most of these problems are going to be symmetrical. So if you accidentally went to a different interval of consecutive zeros, you'll get the same answer. Okay, let's go for 5 more minutes, and then I'll tell you what homework assignment I want us to do. Everybody okay with 3 and 4?
If you have everything there, then that'll be okay.
Did my key have anything further?
Yeah.
Okay, that's fine. That's fine. As long as it's equivalent, I'm okay with it. Okay.
Like our squared equation. Oh, wait, you didn't have a square.
Right, yeah, this is already R squared, so yeah, that's a little bit strange there. Yep.
On number 5, like on your answer, I got negative. Actually, but I'm trying to look, it looks like I.
What did you do for your bound?
I pi 4 and 3 pi 4 3 pi 4.
Yeah, I've also done it.
I don't see any difference in what you wrote down there from what I talked to.
Yeah, let me look into that. I don't know if I converted that to a negative, from a negative to a positive. But yeah, let me get back to you on that. I'll look at it in more detail. Maybe something is causing that negative to appear. I'll look at that. But we're always looking for positives, so hopefully it's just as easy as just changing any weird negative values to positive, but let me confirm that, work it out and let you know.
One thought that comes to my mind is the fact that given that R squared, so it's the square root and then squared, that kind of has like absolute value sort of different causes become positive.
Hmm. Yeah, that R squared may do something to the curve that we're not expecting. Okay. Okay, let's revisit this problem later. Okay, let me give you your assignments. We're gonna try to get through this packet by next Wednesday so that we can begin doing our test review. So tonight you're gonna be working on page 43 to 47. And I'll send out a daily reminder since this is not in your calendar. And then Friday, assignments for the weekend is page 48 to 53. And then Monday's assignment, page 54 to 60. And then Tuesday's assignment, 61 to 68. And then even as we start unit 10, we can still kind of steal some time to continue reviewing. And your test is not next Tuesday, but the Tuesday after that. And I'll start holding some help sessions probably starting next Wednesday, Thursday, leading up to the test if we need it. All right, come get your phones.